Hey guys, Joe Pye here at Advanced Innovations, Austin, Texas. Welcome back to the shop. Welcome back to the infamous whiteboard. It's been a while. Today's video is going to be about how to make a dog bone feature on a rotary table without goofing around and needing a whole bunch of peripheral support gear. Do it the easy way. Before we get to that, there are a few things, a few terms that I need you to understand. And these are valuable things to understand. So let's just get right to it, right? Up on the board. First thing, the square root of a number. What is the square root of a number? Well, that is the number when it's multiplied by itself times itself equals the number that you're looking for the square root of. What did he just say? I have no idea what he just said. All right, number. Here we go. 9. Number 9. What is the square root of number 9? Square root of 9 is 3, okay? Easy. This is basic, but you get it. Square root of 9 equals 3. Okay. Thank you for watching. Okay. All right. Square root. Now you know what a square root is, right? It's the number that multiplied times itself equals the number that you're looking to get the square root of. What is a squared number? Not a square root, a squared number. A squared number is the number times itself. This is 3 squared. That's all you got to know. That and one more thing, which is called the Pythagorean theorem. I know some people say Pythagorean, but not in this shop. All right, here we go. Pythagorean theorem. A squared plus B squared equals C squared. Now that is really helpful in figuring out the sides of a triangle. It's not going to give you the angle of a triangle because for doing a dog bone feature on a rotary table, you don't need an angle. Unless, of course, it takes off at a different angle from, I'll show you. What does this mean? Here's your triangle. Nice and big. Now bear with me, I'm going to check the focus so you see this. All right, close enough. A squared plus B squared equals C squared. Let's call this is A, this is B, and this is C. And I remember the ABC combination of altitude, base, and climb. Word association sometimes helps, right? Altitude, base, and climb. Actually, the C is also called the hypotenuse. So let's put some numbers here. 3, 4, what is this one? What is that one? Who knows what that one is? Let's figure it out. A squared plus B squared. So that's 3 times 3 equals 9. B squared is 4, right? 4 times 4 equals 16. Total of that is 25. So C squared equals 25. So we need the square root of 25 to figure out what that is. The square root of 25 is 5. Boom, boom, boom. 5. Okay. I'm going to fade out here for a second. Okay, I'm back. Sorry about the glitch. Got a CNC running. Had to check it. That is really important. If you haven't mastered this yet, figure it out. Remember it, lock it away. It is incredibly valuable for rotary table work and a lot of other applications as well. So if you have that little squiggly thing on your calculator, it looks like this, and you don't know what that is, well, that is a square root symbol. So if you hit that square root symbol and then type in a number and hit equals, it's going to give you another number, and that's the square root of that number. All right. Now that you know the Pythagorean theorem, I'm going to give you some basic geometry that's just, well, it's basic. Two circles. Not bad. Oh, this should be touching, all right. Kind of important for the exhibit. Okay, two circles of different sizes. What does this mean? Well, this could be the end round feature on the part that you're making and the diameter of the cutter. Now, it is impossible for the distance from the center of two different circles to be any greater than the combination of the radius of each circle combined. There you go. Radius of one circle plus the radius of the second circle gives you the distance between the centers of those two circles. Now that's important. It really is important. Okay, there it is. And the tangent point between two circles or two arc features, the tangent point is a straight line between the centers of the circles and the tangent point. Straight line. Forever and a day, right there. Zoom. Now we're ready. Here it comes. Got it? I'm going to draw a dog bone feature up here, and I'm going to show you how the math just presents itself, and you don't need Dykem blue, you don't need a height gauge, you don't need gauge pins, you don't need a jeweler's loop, you don't need to guess, because everything is there for you. If you have dials on your machines with numbers, and you have a calculator, and you have 2 minutes, do this. Here's your part. That is the round feature on the end of the part. Let's just say for yucks, there's a hole in the center of that part. Just say. Center, right? Now the neck of the part. I don't care if the neck of the part is straight like a dog bone would be, or it flares out to match a bigger diameter on the other end. There will be a minor diameter probably on the print. So let's just strike a center line in here. And put that in there. Radius. Okay. This is a dimension on the print. That's a given. This is a given. This is a given. You have everything you need right there, right in your face to create this. Let's put some numbers on it just for yucks. Let's say this is 2 inches. Imperial, or 25, 7, 21.4, 51.4 metric, 2 inches. Let's say this is 1 inch. Now let's make it something different, 0.8. 0.8 on the radius, 2 inch on the diameter, which means 1 inch radius. So we know the point of tangency right here. Coming down from the center. Center to center. You can see the triangle coming out of here, right? There it is. This leg right here is 1.8. 1.8 because 1 inch radius, 0.8 radius, 1.8 total. Now that's going to be the hypotenuse. That's going to be the climb. So let's put that over here. Where are the other legs? Well, the other legs are simple. let's say this is 0.6 across here, per the print. That means from the center line of that part out, half that 0.6, 0.3. Okay. So if we strike a perpendicular to the center line, we have half of the neck feature plus the radius, because there's your tangent point right there. So you have 0.8 plus 0.3 combined gives you the altitude of 1.1. So the only thing missing at this point is the center to this contact point right here. This is where you plug in the Pythagorean theorem. And remember that this is C, this is A, and we're looking for B. So you run the entire equation with the missing integer, variable, number, value, and work it out. Give me a second, I'm going to go grab a calculator. I'm going to work this out on the board for you because I didn't prepare it ahead of time. I'll be right back. Okay, let's look at how this is going to break out and tell you exactly where to put your tools. Using the a squared plus b squared equals c squared, make yourself a little equation. Simple. Don't let the word equation freak you out. Just stack up a bunch of numbers and take a look at what happens. A squared, 1.1. 1.1 times 1.1 equals 1.21. We don't have b because that's what we're looking for. So let's take c. Let's just jump right to c. C squared. 1.8 times 1.8 equals 3.24. Now, whatever b is, added to the first one has got to equal this. So just subtract a from c, and that gives you b. The value of 2.03. Whatever this works out to equals 2.03. How do you find it? Well, that's the square root of that number. With that little funky lightning bolt key on your calculator, hit that button, put down 2.03, boom. It's going to give you 1.4247. A little crowded, but there it is. So this distance right here, 1.4247. I'm going to call it 8. 1.24247. 1.425. Let's call it 1.425. Now there's your moves on your XY dials on your machine. Shift down and over, pop a hole, move back across, down and over, pop the other hole, blend them. I'm going to show you a rotary table blend because as you're coming around for a specific number or increment or angle and you say, I don't know where to stop, I'm going to show you how not to worry about that. One side will be a climb cut, the other side will be a conventional cut, but you fade away in between those cuts and you blend them seamlessly, and nobody ever knows that you did it. So let's take this knowledge out to the mill, apply it, let's make a part. For sake of the actual practical demonstration, these are the numbers I'm going to go with. 900 diameter on the end, a 400 neck, and a 250 radius because I'm using a 500 cutter. This is the math involved. 0.7 on that leg, 0.7 times 0.7 is 0.49. 450 here, because that is 250 on the radius plus 200 on the neck. Squared is 202.5. And the difference between those two is 287.5. Square root, boom, 536. That's my X and Y. 450 and 536 accordingly. Let's do it. Well, the setup of a rotary table is half the battle in producing the part. And the part that I'm going to cut right now for this example is 1 inch wide. And I want to put the center of the table directly over the center of this part, 500 in from both edges. My stop rail on the back is set so that the vise can slide, and that is about the only thing we know at this point. So I'm going to stick in my alignment tool. Little selfish plug here, guys. This is an AI product. Available on the website. All right. I want the back side of this jaw 500 away from center. So we're just going to use the 500 side of the tool for that. Come on down. All right. Locking down the vise. The rotary table is true to the center of the machine at this point. Stationary jaw of that vise is now 500 off center. That quick. True and square to the machine. Get out. 0. I'm going to move the table towards me 500 so the center plane of the machine moves back. This will make sense in a second. According to my digital, I am 500 off center right there. So I'm going to put the part in. Simple. We'll rest it up against the pin. Tighten it up. And return the table back to 0. Now, if all is well, the center of the machine is directly over my hash marks, which means when I spin this pin, it should be 50-50, which it is. All right, put a cutter in, see what happens. I'm going to show you the fade method. I think you're going to like the fade method because it eliminates the need for any angles. I've pulled back for a wide shot so you can see the rotation of the table versus the rotation of the handle. Now, sometimes this can be confusing when you're looking at the cutter on the part, but on my table, this is a phase 2 10-inch rotary. When I turn my dial clockwise, the table turns clockwise. This is a good thing to know so you don't bury your cutter. As I turn this dial clockwise, watch for this part to rotate this way. Okay? Counterclockwise with the dial, counterclockwise with the table. For the start of this demonstration, make sure the table is oriented to 0. And lock it. First shift on the table is the Y-axis shift. We're going to go for the 536. And we're going to put a spot on either side of that X. If the math that you did is correct, you should now have the neck dimension that's on your print. This should be approximately 400 across, depending on the size of the cutter. Now, I do not have an angle for this, and I'm not going to worry about that. As I rotate the part, I'm going to push the part off the cutter. So this part is initially going to spin counterclockwise so that the cut moves clockwise. The part is moving counterclockwise. The cut is going to move clockwise. Somewhere through the middle of the cut, I'm going to shift the entire table off the rotary. This is a two-handed move. You might have to watch this twice to understand what I'm doing, but watch what happens. This is side number 1. This is the climb cut. I'm going to drop the cutter back in the original pocket. The table is going to spin counterclockwise. This is a climb cut. Halfway through, I will shift the X-axis and push the table away from the cutter. Here it is. Go for a camera angle so you can see what the table did. It actually did shift away from the part. Okay. See the distance between the cutter and the radius? Let's return everything to 0. Let the fog clear for a second. Start over. Next operation is to move the cutter back to exactly where you put this spot face in right here, or whatever feature you created. So let's put it back on the 536 on the Y, and that was 450 on the X. Cutter is now positioned directly over this, and I'm going to make a sweeping counterclockwise cut with this, resulting in a conventional cut with the end mill. When I get beyond center or anywhere into the existing radius, I'm going to walk the table off the feature, and it will look exactly like a continuous feature. Wanna bet? Let's watch. Now for this, I need the table to go clockwise, so the dial is turning clockwise. The part will spin clockwise at this time, resulting in a conventional cut with the end mill. And when the end mill transitions into the area created by the climb cut, I am going to shift the x-axis of the machine, and I'm going to pull the rotary table away from the spindle, resulting in a combination of climb and conventional cuts to form this feature. Let's take a look. That is an extremely well-centered feature. The blend is perfect. The tangents are perfect. No angles involved. A squared plus B squared equals C squared. Boom. Rotary table magic all day long, guys. If there is an angle of run out on either side of this, well, that is another set of equations that you're going to have to figure out based on what the exit diameter is, what the tangent is. So as far as a simple straight up dog bone is concerned, no angles necessary. Voila. How's that for a thumbnail? I like it. Well, I hope you got something out of this presentation. It certainly does make fabricating dog bone features on a rotary table a lot easier. The a squared plus b squared equals c squared is called the Pythagorean theorem, and it usually works on right triangles only. So be aware of that. One of the angles in your triangle needs to be a right angle. And that's usually what you get when you merge two circles and tangent points looking for exactly what I demonstrated. So nail that down in your mind. Remember that. Work it however you need to work it. As long as you have two of the three, you will be able to figure out that third leg relatively easily. The alignment pin that I used is one of our products. Chances are the price is going to go up because guess what, people? Steel's going to go up. So is aluminum. So, ding. Not even going to go there. Well, that's all I got for you. So thank you very much for tuning in. I do appreciate your time. I hope you're well, happy, and safe wherever you are. I'm Joe Pye, Advanced Innovations in Austin, Texas.